We've been talking recently about linear functions, which are polynomial functions of degree 1, and quadratic functions, which are polynomial functions of degree 2. So in this section we'll just generalize. Instead of looking at these specific degrees, let's just look at all polynomial functions and establish some facts about them. And we'll start there with polynomial functions and we'll move on to rational functions in just a minute. But in general, a polynomial function is a function of the following form, or at least it can be written in the following form. F of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus ... count this down until you get to a sub 1 times x to the 1 plus a sub 0. So what am I saying here? Well, this is just sort of the general abstract way of saying that f of x is equal to some polynomial. And that's what a polynomial function is. It's a, it's a function where your rule of assignment is determined by a polynomial. So same rules as before. To be a polynomial, this number n has got to be a positive number and a whole number, so a positive integer, or at least a non-negative integer, I should say, because 0 is allowed. And the same terminology as before, it's the degree of the polynomial. So the highest power that you see is your degree, and all of these guys, the a sub n's, a sub n minus 1, and so on, they're the coefficients. And they are, of course, then real numbers, where my leading coefficient, a sub n, has got to be non-zero. So this is all a polynomial function is. It's a function that's given by a polynomial. So let's establish some basic facts about these things. So for starters, the graphs of polynomial functions are smooth, so there's no sort of sharp corners, no kinks in them or anything, and continuous, meaning you can draw you can draw the graph without having to lift your pencil from the paper, right? There's no holes in it. It doesn't blow up to infinity or anything. And the domain of all polynomial functions is what? Well, this is all the x values that we're allowed to plug in, right? And remember, the only things we're not allowed to plug in, the only things we would look out for is when we divide by 0 or take square roots of negative numbers. And of course we never do that with polynomials, so the domain is all real numbers in interval notation from minus infinity to infinity. And so in general, I have a function with domain all real numbers. It's a nice, smooth, continuous function. In general, polynomial functions just they're as nice as they can be, right? They're nice, smooth functions. They increase, they decrease, they increase again, they decrease again, and so on, right? So they're sort of the graph of an arbitrary polynomial. This is sort of the picture you should have in your mind. Just nice, increasing, decreasing, smooth, continuous functions. There's no sharp corners in here. There's no holes in it or anything like that. Let's see, the zeros. Zeros or x-intercepts. This is perhaps the most important thing about polynomials. So I'll tell you, a degree n polynomial. A degree n polynomial has at most n zeros or x-intercepts. Okay, so this picture that I have up here, how many zeros does this have? Well, this cuts through the x-axis at 3 different points, right? So this cannot be the graph of a degree 2 polynomial, because degree 2 polynomials have at most 2 zeros. This has to be at least degree 3 to be cutting through the x-axis to have at least 3 zeros. All right, so this is one of the most important facts, is that the degree tells you sort of the degree of it gives you a limit on how many possible zeros you can have. And similarly, a polynomial with n zeros must be at least degree n. Alright, so this is what I'm saying up here, right? This has 3 zeros, so it must be at least degree 3 by the same logic. And in fact, I can strengthen all of this. Where is this coming from? Well, how do you find zeros of a polynomial? You set the function equal to 0, right? You ask which values of x make it equal to 0. How would you do that? Well, then you'd have to factor your polynomial. So x is a 0. Or, sorry, I should say a is a 0. How about how we combine the letters? X equals a is a 0 if and only if x minus a is a factor. Alright, if you're looking for the zeros, you're going to factor your polynomial, and then you're going to look for factors like this. X minus a, well, that equals 0 if x is equal to a. So, this is sort of, this is where this stuff is coming from. If you think about how many possible linear factors you can have for a degree n polynomial, well, there's at most n of them. So this is where this is coming from. So the degree tells you something very, very stark about the possible numbers of zeros of polynomials. And I'm out of space, so I'll erase this, but I have a few more facts. So the last thing I want to talk about is the end behavior of polynomials. So what I mean here is what my polynomial does when I start plugging in very large values for x. So coming back to this picture, all this stuff in the middle here, all this stuff sort of for small values of x, I don't care about any of this when I'm talking about end behavior. What I mean is what happens to my function as x gets very large, and you'll look in this case and you'll see, okay, the function eventually just grows forever. It gets larger and larger and larger and larger, and for very large negative values of x, it sort of does the same thing. It grows forever, but in the negative direction. So when I'm talking about the end behavior of a function or of a polynomial, I'm asking what happens for very large values of x. All this stuff near the origin for small values of x, I don't care about it. Yeah, it goes up and down, but what happens at the ends of the graph? So let me tell you. We've got sort of 4 different cases here. Even degree and odd degree. Depending on what your degree is, whether you're even or odd, you'll do 2 different things. And also, depending on whether your leading coefficient is positive or negative. So, positive leading coefficient. What I mean by this is a to the n, right? A to the n, this is your coefficient of the highest degree term. And negative leading coefficient. Okay, so if you're even degree with a positive leading coefficient, you look like, I don't have a whole lot of space here in this thing, but so we've got all this stuff in here, right? All this stuff that we don't care about, but at the ends of the graph, an even degree polynomial with positive coefficient gets larger and larger and larger in the positive directions. So as x gets larger in this direction, it blows up, and as x gets smaller in the negative direction, or larger in the negative direction I should say, it also blows up in the positive direction. Negative leading coefficient, well, think of multiplying this whole thing by -1, that just flips the entire graph, it reflects it through the x-axis, right? That's one of our transformations we know. So again, forgetting about what happens in here, but if we reflect it, it eventually decreases forever in both directions. Odd degree. Odd degree for very large values of x. Well, again, where's this coming from? Well, for large values of x, it's really just the leading term that matters, right? It's the biggest powered term that you see matters, because for large values of x, that's going to be absolutely huge compared to all of the other terms. And when you take an even number and you raise it to an odd power, it becomes very, very large. So this increases in this direction. But if you take a big negative number and you raise it to an odd number, it becomes a huge negative number. So in the negative direction, it decreases forever. And once again, negative leading coefficient, all that's going to do is reflect this through the x-axis. So in this case, we'll be decreasing here and blowing up to positive infinity in that direction. So knowing something about the degree of the polynomials and something about the sign of the coefficients can tell you something about the shape of the graph. Right, coming back to this guy, which case are we in here? I know this must be the graph of a polynomial with odd degree, and its leading coefficient must be positive, right? We're in this case. Let's do an example. So here's my graph. We're told this is the graph of a polynomial, and we want to answer some questions about it. So, for starters, what's the degree of this polynomial? Is it even or odd? Well, looking at the end behavior, right, looking at the shape of this, forgetting about all this stuff that's happening near the origin, as x gets very large in both directions, it decreases forever, right? It blows up to minus infinity. So, the end behavior looks like this. So this tells us it has even degree and negative leading coefficient. What else do I see? I see it has 3 zeros, right? It has an x-intercept right there. Here, it touches the x-axis. It doesn't actually cut through. It sort of touches it and bounces off, but that's still a 0. And here I have a 0, right? So, also, 3 zeros means it's at least degree 3. So I think one of my math lab problems is very similar to this, where it asks, what's the minimum degree of this polynomial? So you look at this and you'd combine this information. You'd say, well, looking at the zeros, I know it's at least degree 3. But looking at the end behavior, we already decided it must actually be even degree. So it has to be at least 3, but even means the minimum degree of this guy is the smallest even number bigger than 3, which is 4. So minimum degree for this particular graph would be 4. This is at least a degree 4 polynomial. Combining those two pieces of information, right? The zeros tell me it must be at least degree 3, but the end behavior tells me it has to be even degree, so combining those two facts, we're looking at degree 4 here. Let's do another one. Not this same problem, but something similar. Okay, so we're given the graph of a polynomial. Looks like this, has cuts through the x-axis at -1, again at 0, and again at 2. And the question is, write an equation for the lowest degree polynomial function with the graph shown. And we're going to use a leading coefficient of plus or minus 1. So let's see, let's read off some information first. Let's go with the zeros, because that's the most direct bit of information here. We've got zeros at -1, 0, and 2. So the zeros are -1, 0, and 2. So that tells me something about linear factors of the polynomial, right? It tells me that it includes at least these linear factors. Factors of the polynomial include x minus -1, x minus 0, and x minus 2. So we'll write this in a slightly nicer order, or a nicer list. This would be x plus 1, x, and x minus 2. Just formatting them a little bit more nicely. What else do I need? Well, I need my polynomial to be odd degree, but if I multiply 3 linear factors together, that gives me a degree 3, so it will be odd. And why am I saying odd, by the way? Well, because I'm looking at the end behavior of this graph, right? Forgetting about all this stuff, I'm looking at the end behavior. This is an odd degree polynomial. And because it goes to negative infinity for positive values, I know my leading coefficient has to be negative, right? So end behavior tells us odd degree and negative leading coefficient. So how do I get an odd degree polynomial with negative leading coefficient and all of these zeros? Well, just multiply them all together. So I'm just about out of space, but all I want to do here is take f of x equal to x plus 1. Let's write the x in front. It'll look nicer. X times x plus 1 times x minus 2. And you'll notice that when I multiply these all out, my leading term will be x cubed. If I want a negative coefficient, I just need to put a negative in front of everything. And I think on my math lab they want you to expand this, so we'll expand this out. This will be minus x times x squared, minus 2x plus x is minus x, minus 1, or plus 1 times minus 2 is minus 2, or finally, minus x cubed plus x squared minus x times minus 2 is plus 2x. And there's our solution. So this is a polynomial of minimum degree, right? Because I need at least degree 3, so we're degree 3, so it's a minimum possible degree. That gives me something with the end behavior that matches this because it's odd degree, and we've got a negative leading coefficient giving me this end behavior. And we've constructed it so that our factors are exactly corresponding to the zeros. Right? We've constructed it so that when you factor it, you have a 0 here at minus 1, 0, and 2. So there's what this problem is asking us to do, and I think there's 1 or 2 problems like this for homework as well. But moving on, let's move on to rational functions. Alright, so next up we have rational functions. Again, another very important class of functions closely related to polynomials because they're functions of the following form, or at least can be rearranged to be written in the following form. They look like f of x equals n of x over d of x. Don't be thrown off by the n and the d here. Remember, we can give our functions any name that we want, so usually we go with f or g or h, but here I'm calling the functions n and d, so n of x, n for numerator, and d for denominator, where n of x and d of x are polynomials. So a rational function is just a ratio of polynomials. It's one polynomial divided by another polynomial, with, again, the condition that the bottom polynomial is not constantly 0, right? Dividing by 0 wouldn't make any sense. I'm not saying the polynomial down here can't have zeros. They usually will, but it can't be a constant 0 function. So anyway, this is a rational function. A rational function is a ratio of polynomials, and that's really all there is to it. So a couple of important facts. Let's see. So again, the graph is smooth, so it has no sharp kinks or corners or anything, just like polynomials do. But it does have discontinuities, and these discontinuities generally come in the form of asymptotes. Sometimes you just have little holes in the graph, but has discontinuities, or asymptotes. Where are these discontinuities happening? Where they're points that aren't in the domain of the function. So when you divide by 0. Alright, so the domain is all real numbers except where d of x, the denominator, is 0. So if you're looking for the domain of a rational function, you just need to identify all values except for, again, as we usually do with domains, we just want to avoid dividing by 0. So it's all real numbers except for the zeros of the denominator. What am I talking about here with these asymptotes? Well, here's sort of what a general rational function looks like. Again, they can come in many different flavors, but in general, when you graph a rational function, you'll have these asymptotes. So here I'm going to draw a graph with two vertical asymptotes. And you'll also often have horizontal asymptotes. So I'm going to throw a horizontal asymptote on here as well. What do I mean by vertical asymptotes? I mean these are points where, again, they correspond to sort of dividing by 0. So that causes my function to blow up. So here I'll graph this, I'll draw something where the function blows up to minus infinity as the x values get very, very, very close to these vertical asymptotes. And then on the other side of it, again, we'll come back from minus infinity. So something like this. And then we have a horizontal asymptote, which means that as x gets larger and larger and larger, our y values get closer and closer and closer to this horizontal line. But don't ever actually quite get there. And then over here, how about I just draw, on this side of the vertical asymptote, we're going up to positive infinity, and then we approach this horizontal line again, this horizontal asymptote. So in general, when you picture the graphs of rational functions, in your mind you should have something like this, right? Something with vertical asymptotes where my function blows up where it's undefined, and then as we go off to infinity in either direction, generally, not always, but generally you'll have these horizontal asymptotes as well. So being that these asymptotes are so important, let's talk about now exactly how to find asymptotes of a given rational function. So we'll start off with horizontal asymptotes because they're actually the easier ones to identify. When does a given rational function have a horizontal asymptote and what is it? And for starters, I'll point out that there's at most one, right? So you can only have either 0 or 1 horizontal asymptotes. And it comes down to degree considerations of the numerator and the denominator. So if the degree of the numerator is less than the degree of the denominator, then you always have y equals 0. Remember, this is a horizontal line, y equals 0, it's the x-axis. If the degree of the numerator is less than the degree of the denominator, then y equals 0, the x-axis is your horizontal asymptote. Meanwhile, if the degree of the numerator is larger than the degree of the denominator, then your rational function, doesn't have a horizontal asymptote. And in the third possible case, where the degrees are equal to each other, then y equals a over b is your horizontal asymptote, where a over b is just the ratio of the leading coefficients of the numerator and the denominator. So we'll do some examples here, a couple of quick examples. All right, so I have in front of me, I have 3 rational functions. The first one is 3x squared plus 2 over 4x cubed minus x plus 1. And the question is, find the horizontal asymptotes. Well, we're in the situation where the degree up top is 2, and the degree down below in the denominator is 3. All right, so we're in the situation where the degree of the numerator is less than the degree of the denominator. So, which case is this? Well, this means that y equals 0 is the horizontal asymptote. And that's all there is to it for these questions. You can ignore the rest of these polynomials. All you care about is the degree. Except in the last case, but we'll get to that. So all you care about is the degree, and the fact is the degree of the numerator is less than the degree of the denominator, so y equals 0 is the horizontal asymptote. Here we're in the opposite situation. The degree of the numerator is 3, degree of the denominator is 2, so the numerator has a larger degree than the denominator. So this is the case where we don't have one. So no horizontal asymptote. And finally, in example C, in this situation the degree of the numerator is 5, degree of the denominator is 5, so the degrees match up, and this is sort of the interesting case, where I have to consider a little bit more now. Now I do have a horizontal asymptote, and the way I find it is I just take the ratio of the leading coefficients. So in this case, the leading coefficient of the first polynomial is 4, and the leading coefficient of the bottom polynomial is 3. So I do have a horizontal asymptote, and it's going to be at 4/3. Y is equal to 4/3. Alright, so finding horizontal asymptotes is not hard. It's just this degree consideration. And in the one case where the degrees match up, you just take the ratio of the leading coefficients. So let's talk about vertical asymptotes. So finding vertical asymptotes is just a little bit more work, but not much, and it involves factoring. So the first thing you do when you're finding vertical asymptotes is just simplify as much as you can. So almost always you'll be given a polynomial, a numerator and a denominator that aren't factored. So the first thing you need to do is factor them. And then you cancel all the common factors. So if there's a common factors above and below, cancel them off. And then you just have to look at the denominator. And what this tells us to do is it tells us that if c is a 0 of the denominator, then x equals c is a vertical asymptote. Which should make sense, right? These vertical asymptotes correspond to when we're dividing by 0. So the vertical asymptotes happen when we divide by 0, and we don't have a 0 up top to sort of balance it out. So for example, find the vertical asymptotes. Find the vertical asymptotes for, let's say, f of x is going to be, we'll go with something simple here. We'll just do x plus 1 over x squared minus 4. So a very simple example to start with. But this is a rational function. It's one polynomial divided by another. So what do I need to do? I need to cancel all common factors, which means I need to fully factor this. The top is of course already factored. It's just this linear thing, x plus 1. The bottom factors very simply. It's a difference of 2 squares. So this is x plus 2 times x minus 2. Okay, so we cancel all common factors. Well, there are no common factors, so nothing to cancel, which means all I need to do now is identify the zeros of the denominator. What are my zeros? Well, my zeros are going to be plus or minus 2 here and plus 2 here. So asymptotes, the vertical asymptotes are x equals plus 2 and x equals minus 2. Let's do another one. Okay, so similar problem. Here's a rational function, x cubed minus 9x over x squared plus 5x, and the question is, I haven't written down the question, but it's find the vertical asymptotes. So once again, we need to fully factor because we need to cancel any common factors if they exist. So factoring the top, we can pull an x out, and that leaves us with x times x squared minus 9. And on the bottom, looks like we can pull an x out here as well, right? So x times x plus 5. So you'll notice we do have a common factor here. We can cancel those x's. I don't really need to fully factor the top anymore because obviously nothing here is going to cancel with x plus 5 just because I can see what it's going to be. But if we continue on, it's going to be x minus 3 times x plus 3. Right, because x squared minus 9 is a difference of 2 squares over x plus 5. So nothing there cancels with x plus 5. We are fully factored, fully reduced, and at this point you can just easily read off the vertical asymptotes. It's the zeros of the resulting denominator. And the zeros of x plus 5 is x equals minus 5. So vertical asymptote at x equals minus 5. So not a particularly difficult process, but again, this is sort of why we were doing all this factoring in the beginning of the semester is, well, there's lots of cases where you'd want to factor a polynomial, but this is one of them. All right, so it's one of these sort of foundational skills you need to have before you can do much of anything else. Once you can factor, now you can talk about, you can solve for rational functions where the vertical asymptotes are. So here's one more function. We'll combine everything together here, and we'll do even more. We'll sketch the graph of this function. So that'll be sort of the end of this, but part A, let's just ask, what's the domain? Well, the domain, all I'm trying to do is find what the zeros of the denominator are. This is different from finding vertical asymptotes, by the way. I'm not sort of canceling anything out or anything. I'm just asking what are the zeros of my original denominator, not necessarily the canceled denominator. So when does this equal 0? Well, this of course factors very nicely. I don't even need to factor this. I could just say this means x squared is 9, so x is plus or minus 3. Notice I could have, what I was saying is I could have factored this. I could have done a difference of two squares and said this is x minus 3 times x plus 3 equals 0, but you get the same answer. X is plus or minus 3. So the answer is the domain is all real numbers except x equals plus or minus 3. Right, as we always do with domains, we just want to avoid dividing by 0 and square roots of negative numbers if they exist, which they don't here. But the domain is going to be all reals except where we divide by 0. So all reals except plus or minus 3. We'll do a little bit more analysis on this. How about what are the x-intercepts? So this will be part B. Find the x-intercepts. All right, how do we find the x-intercepts? That's when y is 0, right? So that's asking what values of x do we plug in that makes this function equal to 0. So we're solving 3x plus 3 over x squared minus 9, 1u equals 0. Well, two ways to think about doing this. One is you could just say I'm going to multiply both sides by x squared minus 9 to get rid of this fraction, which is a completely valid way to proceed. Or you could just remember that the only way a fraction is equal to 0 is if the numerator is equal to 0. In either case, we're solving 3x plus 3 equals 0. So this, of course, immediately gives us, this implies 3x is minus 3, subtracting 3 from both sides, and dividing by 3 means x is equal to minus 1. So that's nice. We have this x-intercept of x equals minus 1. And what about the y-intercepts? Well, there can only be one, because it's a function. So y-intercept. What are we doing here? We're asking what's the y value when x is 0? So we'll plug in 0, and we'll get 3 times 0 plus 3 over 0 squared minus 9. That's 3 over minus 9. Which of course simplifies to negative 1/3. So our y-intercept here is y is minus 1/3. Awesome. So there's part B, finding the x and y-intercepts. C, let's find asymptotes. C, what are the asymptotes of this function? So horizontal. Do we have one? Degree of the top is 1, degree of the bottom is 2, degree of the denominator is bigger, so this means yes, we do have a horizontal asymptote, and it's the case where y is 0. It's the x-axis itself. And vertical, remember we need to fully factor this, so let's factor this. This is 3 times x plus 1 over, the bottom is the difference of two squares, x minus 3 times x plus 3. We have no common factors, it's nothing to cancel, so now I just have to read off the zeros of the denominator, which are of course plus or minus 3. So we have two vertical asymptotes at x is plus or minus 3. So the last question now is going to be, let's sketch the graph of this. This is really why we're doing this, right? We want to be able to envision what these graphs look like. This is a very sort of important skill with functions, is knowing what the graphs look like, because the graph tells you everything there is to know about the function. So instead of just writing down all these lists of things, let's try and graph this. And we'll need a little bit more information, but we should be able to graph this. So lastly, let's sketch a graph. Let's see. We had two vertical asymptotes, right? We had vertical asymptotes at plus or minus 3. So let's say this is happening at minus 3. And we'll put another one here at positive 3. We have a horizontal asymptote, which is our x-axis. So there's the horizontal asymptote. We had an x-intercept. There's only one of them. It was right here at minus 1. So I know I cut through the x-axis at minus 1, and that's the only place I cut through the x-axis. And we also have our y-intercept is minus 1/3. Okay. So I want to graph this. There's a problem. There's quite a few possibilities here. For example, I know I cut through the x-axis here, and that's the only place, and my function has to sort of blow up to this vertical asymptote, but the question is, do I do something like this, or do I do something like this? Right, because there's two different possibilities, and I have to rule them out. And it turns out the best way to do this is really just to think about plugging in a value. So how about I just take a value, something very, very close to minus 3. How about I plug in, say, f of minus 2.9. Alright, minus 2.9 is something very close to minus 3. I've gone ahead and done that. I've gone ahead and plugged in minus 2.9. So you'll plug that into this function, 3 times minus 2.9 plus 3 over minus 2.9 squared minus 9. And I get that this is about 9.66. Okay, so what does that mean? That means when I plug in minus 2.9, it takes on this big positive value, 9.66, which means that I can't be doing this, I can't be going down. My function is in fact increasing as we get close to minus 3, so it looks like that. What about on the other side? On the other side, it has to pass through this y-intercept here at minus 1/3. And now there's questions, what does it do? Does it sort of increase like this? Does it blow up to positive infinity on this side, or does it decrease down to negative infinity? Well, I can answer this without having to plug in any numbers, because I know that this is the only point where it crosses the x-axis. Also, it's continuous through here, so it can't cross the x-axis again and go up to positive infinity. It must do that. Awesome. What about the rest? I don't actually need to plug in any numbers here, I don't think. I know I have an asymptote, a vertical asymptote here, horizontal asymptote here. What happens for very large values of x? Let's just say in our mind, let's plug in, say, x equals 1 million. What do I have? I've got a positive number on top, 3 million plus 3, over a million squared minus 9 is, again, a positive number over a positive number is positive. So out here for very large values of x, I know my function is approaching the x-axis, but I know it's also positive. So it has to be above the x-axis, and it never crosses it, because this is the only intercept. So if it's above the x-axis and never crosses it, it must look like that. And I think we can play the same game on the other side, take very large negative values for x. So negative a million. Here I would have a big negative number over negative a million squared is a huge positive number, minus 9 is still positive. So negative over a positive is negative. So I know it's very, very close to the x-axis, but it lives below the x-axis. It's a very small negative number. So if it's going to be below the x-axis and it never crosses it, then it can't blow up this way. It must take on a shape like this. And this is a pretty accurate sketch. This is basically what it looks like. This is the graph of y equals 3x plus 3 over x squared minus 9. So almost all of the information came from just identifying what's our y-intercepts, or what's our y-intercepts, what's our x-intercepts, what are the vertical and horizontal asymptotes, and from there, if you still can't figure out exactly what the shape is, just go back to what we've always done to plot graphs of functions, or what you can always do, is plug in a few values. Plug in as many values as you need, and then connect the dots. But in a nutshell, that is rational functions. Again, a very important class of functions. It's one polynomial divided by another. Thanks.